given few talks in this FTP. So he's expert in plasmonics, photonic integrated circuits, quantum optics, and self-assembly. And he's mm, familiar with today's topics also. And there is a change. Like earlier, today's lectures were planned to be delivered by Mr. Akash Ben from DRDO Pune, but due to some problems, he could not join for the lectures. And thanks, Dr. Vaibhav, for joining us for these lectures. So, and without taking much time, I would like to hand over. Okay, before handing link over to the speaker, I would like to announce that we will announce the third quiz just after the course. So possibly Friday evening, the third quiz will open. Not only the third, we will try to open first, second, third. 3 quizzes, Friday to Friday. So something like 1 week you will have, although this is Diwali, but sufficient time will be there to attempt. As per your convenience, you can attempt the quizzes. So no need to panic, no need to worry. Quizzes will remain open until you attempt them. Okay. So so that's all from my side. I hand over to Dr. Vaibhav. Please continue your lecture.
Yeah, thanks a lot, sir, for the introduction. And I will try to share my screen. I hope it is visible.
Yes, sir. It is visible and it is in full screen. Everything looks good.
Okay, okay. Thank you, sir. Okay.
Okay, sir.
So, yeah, today's topic is about atomic magnetometer. And we will talk about the development of the atomic magnetometer and what is the need to have an atomic magnetometer. And finally, we will go a little bit into the application aspect, and I will try to discuss two main applications of the atomic magnetometer. So actually, there are different kind of magnetometers which are available. And here you could see the name of the magnetometers. So for example, you might be aware with the name ISQUID. These are superconducting quantum interference devices. Then there are these Hall magnetic sensors, which works on the Hall magnetic effect. And in the very bottom, you could see atomic magnetometers. Now, depending on the size, so the size of atomic magnetometer, the overall size of the device is roughly 12 mm. And you could see that in terms of size, this proton magnetometer is quite small, and TMR is also very small. So TMR is tunnel magnetosensor. And depending on the cost, SQUID is quite expensive, and these atomic magnetometers is okay. So they are roughly $12,000. They can actually measure up to femtotesla level, and you see that in terms of sensitivity, they are actually one of the best. So the another best one is SQUID devices, but these SQUID devices comes with a heavy price. Another problem with SQUID devices is that you have to maintain a very low temperature. But in case of atomic magnetometer, you can actually work at room temperature. So as you see in the advantage section, you does not require cryogenic cooling. That is one advantage of these atomic magnetometer. And definitely sensitivity is quite good. And there is also disadvantage, and one of them is that you have limitation from the atomic vapor side. So there is some performance based limitation, some noises which comes due to the collision of the vapor. We will talk about that in a minute. So this is just a brief overview what is available in the market in terms of sensors which are based on magnetic effect. So once these PPTs are circulated, you can have a close look to this as well. And in today's topic, we are going to dive deeper into the atomic magnetometers. So, in order to make these atomic magnetometers, we use some vapors, or let's say we use alkali metals. So, these are the ones. Usually, we use rubidium, cesium, and they are preferable choices. And if you look this rubidium, cesium here on the periodic table, this is how the rubidium looks like. So for rubidium, you have nucleus, and when we say alkali atom, that means there is only one unpaired electron in the outermost shell. So you can also see rubidium's atomic number, and according to that, you can start writing the shell structure 1s2, 2s2, 2p6, and all that, and then you will end up with 5s1. So there is only one electron in the outer shell. Um, you might also be aware that the shape of these atomic orbitals, they look like this. So this is s orbital, these are p orbitals, they have some sort of probability distribution. So if you see in terms of quantum mechanics, that's a probability distribution, that what is the probability of finding an electron in the p orbit. And similarly for d and f, there is different probability distribution. So in the atomic magnetometer, which we are going to build or we are going to study, we will use rubidium. You could use other as well. You could use cesium as well. That is no problem. You could also use potassium. Um, so in terms of atomic magnetometry, there are three basic principles on which these atomic magnetometers work. One is coherent population trapping. So it is some sort of trapping of atoms inside. The another one is nonlinear magneto-optic rotation. And the third one is SERF regime. So this regime gives the highest sensitivity, and we are going to discuss only this particular one. Then this one is actually based on completely optical phenomenon. So that's why I have named it optical atomic magnetometer. So this, as I said already, gives very high sensitivity, works on room temperature, and you can actually make them very small. So this is one example that this is how it looks like. So that is atomic magnetometer on a chip scale. So just to give you an idea that this is roughly 12 centimeters. So like the normal scale, you have 15 centimeter, and this is roughly the size of scale. So people have gone to these limits. In the beginning, they were quite big, size of a room, and then slowly going down miniaturization, and finally you are at this level. So as I already told you that there are different regimes. So there's CPT, NMOR, SERF. So here there is a comparison between all these regimes, and what we are going to study today is this Handley or SERF regime. And I will try to explain you the principle, how we build this device. And for more interest, you can actually look into other devices as well. So here is the comparison table which is given. So if you look at the sensitivity here in femtotesla per square root hertz, you see that the sensitivity for this device is roughly 0.16. This NMOR provides a bit higher sensitivity, and the CPT provides even higher sensitivity, but then the problem is that they cannot do vector measurements. So there is some other problems which we will going to discuss. So just to give you a basic idea, what kind of signals are we targeting? So you know the magnetic field, Earth also has a magnetic field, and these magnetic field is in the range of microtesla. So here is the signal strength. So this strength is in microtesla. Then human has a heart, right? We all have has a heart. And if you go close to our heart, like if I place my hand here, there will be some magnetic signal, and this magnetic signals are in picotesla range. Then you all know that in our brain also we have neurons, and these neurons have electricity or electrical signals, and because of that, like for example, we go for MRI, magnetic resonance imaging. So in the MRI or fMRI, they use magnetic field. So the human brain has a magnetic field roughly in femtotesla, 10 to the power minus 15 Tesla. And the best atomic magnetometers can um, sense up to attotesla. So the range has been really 10 to the power minus 18 Tesla is people are able to measure. So just to give you an idea that what is Earth gives us, what is close to the human heart, in the human brain, and then uh, autosecond. So now let's try to discuss the mechanism of atomic magnetometer. So suppose if you want to build atomic magnetometer, what is the basic principle? So the principle is not very complex. It's a simple principle. So rubidium atom is there, and this rubidium atom has some sort of spin associated with the atom. What you have to do is you have to apply a laser, and this laser has to be circularly polarized. We will call it a pump beam. Once you apply the circular polarization, the rubidium atom will try to align its spin in the direction of this wave propagation. You have circularly polarized light, you hit to the rubidium atom, and the atom aligns its spin in the direction of the propagation. Now you have to apply one magnetic field, which in the end you want to detect. Once you apply that magnetic field, the spin of this rubidium will tilt, and there will be some sort of orbital motion, and there will be a frequency associated with this. So you can understand that you have a magnetic moment, and then you have applied some field. So mu cross B, you do the thumb rule, and the B is outside. So definitely this spin is going to circulate in this direction. This frequency is called Larmor frequency. And the spin is now not in this direction, but it is somehow deflected depending on the magnitude of the field. Now what you do is you take another laser, and the direction of propagation of this laser is perpendicular to this laser. So if this is going in X, you have to go in the Y direction. And this laser also has a polarization, but this is a linearly polarized laser. And once this laser passes through this rubidium medium or hit this rubidium atom, because of the spin of this rubidium atom, the polarization of the beam will deflect. So this was the initial one, the dotted line, and now it will become something like this. So you can detect this polarization rotation. That is one way. The second is the intensity of this light will also get decreased. So you can either try to measure the rotation of the polarization, or you can try to measure the decrease in the transmission. And by doing any of this, you are able to measure how much magnetic field was there. That is the basic principle. Just to explain you again, in a this was a very microscopic, just going to one atom, but on a macroscopic level. So let's say there is a glass uh, cell. In this glass cell, there is a lot of alkali vapor. So this is rubidium vapor, and each of these rubidium atoms, they have spin, and this spins are randomly oriented, right? Once I go with the circularly polarized pump light, all these spins are aligned in the direction of the light. And once I apply a magnetic field which is out of the screen, because of the magnetic field, this spin will deflect. All of them will deflect in a particular angle. And then you come with a probe beam, and this is the probe beam. I told you, if you apply pump here, you have to go with the probe beam with this direction. This probe beam is having some input polarization, which is linearly polarized. Because of the interaction with the atoms, polarization of this beam will deflect, and then finally you have to measure this deflection. So that is the basic principle. Again, just to give you even more clear understanding, there is a very nice video on National Institute of Standards and Technology, NIST, US department. So if you want to go more deeper into quantum-based sensors, that is a quite good website. You can actually have a look there. There is a lot of material available. So here I will play this video for you. And what you see in the video is that's a cell. It's like a glass closed glass cell, And inside this cell, there are rubidium atoms. And all of these rubidium atoms, they have polarization or spin in different directions, right? So spins is randomly oriented. Um, Now what you see is that you come up with a circularly polarized light, and this light will align the direction of the spin in its propagation direction. Now you come up with a magnetic field. This magnetic field will deflect the spin, and finally this will decrease the amount of the transmitted light. So this transmitted light will get decreased, and then you can, by doing that, you can measure how much field was applied. So this is a bit different way. They did not apply a probe beam, but just by using a single beam, they were able to measure. So now let me go a little bit more. So slowly we will try to go now a bit more deeper in the microscopic picture. So macroscopic is done. We now know how it works briefly, like the overall overview. But now I will try to go deeper into it. So I hope this is clear to you, or just to briefly remind you that what we have is, let's say I have an electron. This electron has a spin associated with it, which is called the electron spin, and we denote this with the number S. The another thing is that this electron is also orbiting around the nucleus, and because of that, it also has orbital angular momentum denoted by L. Then together S plus L, they makes total angular momentum, and the electron is moving and also orbiting, right? Moving on its own axis and also orbiting. Now you also have a nucleus, and in some isotopes, some materials, this nucleus has a spin. In some it does not, but in some it has the spin, which is called nuclear spin, denoted by I. Now the total angular momentum is this J plus I. So S plus L plus I, this becomes total angular momentum of the atom, right? That is F. And usually people denote it, I mean, this is a typical denotation, how you write it. And that is what is written here, 2s half, 2p half, 2p3 by 2. So in rubidium, we have s orbit, we have p orbit. And what is happening here, these are called fine structure splitting. So p is getting splitted into 2, and s is getting splitted only into 1, or there is no splitting. So this fine structure splitting happens because of the electron spin and the electron orbital motion. So this spin and its orbital motion, because of that, this splitting happens, which is called the fine structure splitting. Now, this particular whole momentum of spin plus this angular rotation can also couple with the nucleus. So total angular momentum is spin plus orbital. When it couples with the nucleus, this is called hyperfine splitting. So you could see that now this level is also splitted into further levels, and these are called hyperfine splitting. Once you apply some external magnetic field, then this hyperfine can also be splitted further. So what you see, this is the ground state. As this state, first fine splitting, so 2s half. Then this 2s half is divided into 2, which is hyperfine splitting. This happens because this s orbit electron is coupling with the nucleus and creating hyperfine splitting. Now if I apply external magnetic field, this bottom level I divide into 3, 1, 2, 3, and this top level I divide into 1, 2, 3, 4, 5. Why? Because the nuclear spin in this case is 3 by 2, and if you see I is 3 by 2 plus half, so F will come out equal to 2, and in this case I minus half, so I was 3 by 2. If you subtract half, you will come out as 1, and these values goes from minus to plus. So minus 1, 0, 1, and here minus 2, 1, 0, 1, 2. So this is just a brief overview what is happening in rubidium atom. Now let's only discuss about this ground level of the rubidium atom. So you see that this one is splitted into five. This hyperfine, the top one was splitted into fine when I apply external field, and this bottom into three. And this is what you see here. The bottom is three, and the top is fine, right? And these two are these hyperfine splitting levels, and they are further splitted. Now the energy between these two is called Zeeman splitting, and actually it is equals to h cut omega L, where omega L is the Lamarck frequency, like the frequency at which this whole magnetic moment is rotating. And you can calculate this by this formula. So the important thing to remember is that these two levels not very much affected by Zeeman splitting, and that's why these levels are actually used in rubidium-based atomic clocks. So if you study atomic clocks, you will find that these are very stable levels, and they are actually even used in satellites and all. Now, what we do in a magnetometer is actually when we apply external magnetic field, because of that magnetic field, this hyperfine level gets splitted into multiple levels, and what we are trying is we are trying to find out the value of this Zeeman splitting. That is actually the value of that external magnetic field. So if you find out how much this splitting is, if you know this value, you apply this formula and then you can actually calculate back what was the applied magnetic field. So this is what we are doing. We are actually trying to find out the Zeeman splitting and the external magnetic field. So I hope up to here it is clear. So this is all about the ground state of rubidium-87. We have somehow understood the basics of the ground state of rubidium atom and the Zeeman splitting of that. Now suppose I take this ground level, which is 2s half. Remember, this is 2s half. And I take this level 2s half, and suppose there are a lot of rubidium atoms, so some will be present in mj minus half and some will be present in m. So mj is just the projection of j into the quadrature or into the measurement direction. So these are just projection vectors. So these you can further split according to that. So just assume that in 2s half you have these two levels, and actually the probability of having rubidium atom in this one and this one is roughly equal. Nobody is telling them to go into this one or that one. So you will find, if you take this glass well, there are millions of rubidium atom. Half of them you will find in this state and half of them you will find in this particular state. What does it mean? That some of them have a different spin and some of them has a spin plus half or minus half. Now what we do is that we excite this state with a circularly polarized light. And what this circularly polarized light has, so circularly polarized light has the momentum which is the value plus 1. So if I add minus half with plus 1, the total will be plus half. So they will go in this particular state which is representing plus half. If these ones take a circularly polarized light, so half plus 1, which is 3 by 2, there is no state which is corresponding to 3 by 2, so they cannot move up. Only these ones can move up once you apply the circularly polarized light. So that is the main idea to apply circularly polarized light. So if you apply right circularly polarized, all the photon have angular momentum plus 1 along the axis in the unit of spin angular momentum, which is h cut. So all of them has a spin angular momentum of plus 1, right? And associated to that, this is the level, they will go there. This cannot absorb these photons because there is no another level. So what happens is that the population here will decrease and you will find more population in this particular level, and whatever was there will remain there. Actually, our final aim is that we try to remove everything from this level and we want to bring them in this level. And in a way, then all the aligned plus half. So this is the main target, is that from the minus half, we want to make the spin plus half. So up to now, we have sent them to excited state. Now there are many interesting things which happen and which creates a lot of issues. Uh, the so this is the very first basic thing, that they will try to go back via spontaneous emission and then they will come into this state. But nobody is stopping them to go here as well, or to go here. So we will try to go now a bit more deeper into this. So we will try to understand what are the depolarization challenges and what are the solutions for that. So the very first thing which creates depolarization. What is the meaning of depolarization? We have a cell. Inside that cell, we have a lot of rubidium atoms. All these atoms have spin aligned in particular direction, but once some collision happens, that spin direction changes, and we don't want that, because if spin changes, the overall coherence time changes, and the things will not be in coherence. And once the coherence is lost, and then our system will not work. So we want to avoid these kind of collisions. So let's say this is our magnetometer cell, this box, and we have these rubidium present inside, right? So what rubidium can do is rubidium can actually collide with these walls. So in order to prevent that, we insert some sort of buffer gases. For example, helium, xenon, and all these gases try to stop the hitting to the wall. So they will still hit the wall, but at least let's say millions of atoms are there. Somehow we would like to reduce it. So in order to reduce that, that is the solution, that we insert the buffer gases. Um, Now, collision with the buffer gas, atoms can also depolarize, right? So once we introduce this buffer gas, they can also collide with the buffer gas rather than collision with the wall. But this buffer gas is necessary to stop a lot of collision with the wall. So you will slowly you will understand my point. So you remember that some of the atoms were present here, and most of them were in this plus half state. This is the ground state. And in the excited state, some went there because of this circularly polarized light, right? Now, when they are in the excited state, actually they are in the p orbital. And this p orbital has a quite long spatial extent. So it is something like this. It has a directional character. On the other hand, the s is spherical in nature. So what happens is that in this case, when these excited atoms are there in the p orbital, which has a quite large directional extent, they can actually collide with this atom. So once rubidium go close to the helium, they kind of make an atom, and now these excited state atoms can also uh, some other rubidium atom can come closer and try to hit this whole molecule. So once they make the molecule, they start to rotate, and then some other rubidium atom can come closer and try to hit this molecule. And this makes this gas more susceptible uh, to the collision. Uh, and because of that, these Zeeman's level get mixed actually. So because of that mixing, some of these atoms will also move into this location. So so the whole thing is that we don't want a lot of collision with the wall. In order to stop it, we put helium or xenon gases. Once we introduce these gases, rather than hitting the wall, the rubidium start hitting with the gases. Now, once rubidium hit the gas, at a very short time interval, it makes sort of a molecule. So rubidium plus helium, they are both atoms, they mix together, make an molecule. And because now some other rubidium, which is let's say sitting here or there, can also hit this molecule. And because of that, whole excited state atoms, their Zeeman splitting get perturbed, and then they will also move in this location. And this is called collision mixing. So Zeeman level mixing or collision mixing. This is one way that that problem can happen. That okay, rather than just stay here, they are now also going in the another one. So just to repeat again, we excited with the polarized light. Most of them went there. Nothing happened to these ones because of the angular momentum. It was not favorable transition. And because of Zeeman splitting or Zeeman mixing, some of them moved here. Now, once they are there at the top level, they can actually come back like via spontaneous emission. So things which are here, they can go either there or they can also go there, right? Things which are sitting there, they can also drop down either here or there. So once this spontaneous emission happens, it happens via emitting a photon. So what happens is that they emit a photon, but this photon emission is random process. So they emit a random polarized photon. I mean, they emit a random photon which is not really polarized in any direction. So suppose one of these rubidium atom comes down here and then it emits a photon. What happens if that photon is taken by some other rubidium? So this unpolarized photon can be again absorbed. Let's say some rubidium is here. This photon comes and then this rubidium takes this photon which was unpolarized. Actually, this is unwanted. We want that these rubidium should take only this circularly polarized light, pump light. We don't want them to absorb these kind of photons. So we have to stop it somehow. And in order to prevent that, we add another gas, which is called quencher gas or quenching gas. This is nitrogen in this case. Now again, the same story. Now they can actually collide with nitrogen, but at least we don't want these kind of photons. So what these photons do, they give their energy to nitrogen in terms of vibrational or rotational mode. So there are different mode of energy, vibrational energy, rotational energy. So this photon, it has some energy. It came out due to spontaneous emission process. Its polarization is not defined, it's undefined. And that's why this photon is unwanted. We don't want it. And we have to get rid of this photon. So what we do is that we insert some gas which can actually capture this photon. So the energy of this photon is somehow related to the rotational and vibrational level of the nitrogen, and that's why nitrogen will capture it in terms of heat. So in a way, now we don't have radiating resonant photon. So we don't have a photon which is unpolarized and have the similar energy level so that it can get absorbed again. So you see, we had a problem and we solved the problem by entering the nitrogen gas. So that is the thing. There are two types of gases present, buffer gas and quenching gas. And there's an equal probability of decaying to the Zeeman level of the ground state. So as I told you, they can either come here or come here. But most of these atoms now will decay to this particular state. Because they, so now let me go to the next slide and let me show you what happens. Like if you keep repeating this process, so in the end, you will end up this whole state. Nothing will be present there, and all the atoms will present in this particular state, which is equal to up polarization or spin up. And that means you have now converted all of your atoms inside this magnetometer cell into one particular direction. So that's the whole cycle. Just to give you a repetition. So in the beginning, they were present here as well, and they will present here as well, the rubidium atoms. Then you come with a pump, which is circularly polarized. So only this transition is allowed. They can go from here to there. And this, they will not absorb the circularly polarized light because half plus 1 is 3 by 2. There is no level which can take 3 by 2. Now, the second thing is collision mixing. So some of these guys can go there and it is vice versa, and some can come here, right? And one, they can also decay back here or they decay back here. And from there also they can decay by emitting some photon. This photon is unwanted. We don't want it. That's why we put nitrogen gas in it. And this nitrogen gas will absorb those photons. So if you keep repeating this process, in the end, you will see that even if something is here, again, you are keep giving the pump. So either they go there, then they come back, or they go from here to there, then they come back here. So if you keep repeating, in the end, what will happen is that nothing will remain there. They all will come to one particular spin state, which will be spin half, and this will be in the direction of the pumping. So they will all align in one particular spin. So I hope I have convinced you that that is the basic mechanism, the core mechanism behind how you convert all of this by incident polarized light. So inside this magnetometer, I told you there are different things available. So you have nitrogen, you have helium, you have rubidium atom itself, and you have some photons as well. So and you are also aware that if you do this pump beam, and this is the B, which is the magnetic field, and this is your total polarization of the rubidium atom. So inside the whole cell, there is a lot of rubidium, and the overall spin is something like this. This total spin in one particular direction, or let's say the polarization. In the end, it is the polarization. If all the spin is oriented in one direction, the polarization becomes in that particular direction. Now, there is an equation which defines how this P changes with time. So actually what we want to know is that what are the factors which changes this P. So here in the left we have dP by dt, meaning the change in P with respect to the time. So what happens is, very first thing, as soon as you have electron in the rubidium, this electron is also rotating here with Larmor frequency because you have applied a magnetic field and mu cross B. So because of that, there is a Larmor frequency, and that is this term P cross B here. Rather than mu, you use P because P is not for a single one, but for the complete ensemble. You have the polarizability P. That is, let's say, in a way, it's a magnetic moment. And this is this term, right? Um, So this depends on the pumping. If you do more pumping and you apply a particular field, there will be a lot of this will keep happening. So depending on the magnetic field. Now, the another thing which can happen is collision between rubidium. So there are a lot of rubidiums. They can also collide with each other. And once they do, in the beginning, let's say the spin was aligned. After the collision, they will create decoherence, or they will try to misalign in other direction. So that is called spin distraction, which is denoted here with ST. The another thing which could happen is rubidium nitrogen collision. So these two collision can also happen, and this will also destroy. So this was rubidium, this is nitrogen, and after the collision with nitrogen, it changes its spin direction. And this is denoted by this particular term, spin distraction. The third thing which could happen, even after adding the buffer gas, they can still hit the wall. After hitting the wall, they again change their spin, which is denoted by this. The another factor is that the photon, and this is the photon of the probe beam. So the photon comes and light is absorbed, and then you see that the spin is changed. So that is given by this particular factor P here. And this is due to the probe beam. So similar thing can also happen when you do use the probe beam. So these are all the parameters which define the total decoherence into the system. And what you want in the end is very less decoherence. You do not want to change the overall spin state. Now, I told you that I will only discuss about spin exchange relaxation free regime, SERF, SURF regime. So here I will take some time and try to explain what is this SURF regime. So in this one, actually, we work below this particular limit. So on the next slide, we will try to explain this. But here, I hope it is clear to you that what are different factors which can create decoherence, and somehow we have to mitigate. You cannot avoid them completely, and that is the reason in the beginning itself, when I showed you that table says that in atomic magnetometer, alkali metals such as rubidium, their vapor phase creates some sort of problem in terms of minimum detectivity. How much magnetic field you can detect, that is depend on how is the distribution, how densely they are packed, how scarcely they are packed, and all that. So now let's try to discuss this spin exchange relaxation free regime, so SURF regime. Remember, we had this ground state of rubidium, so hyperfine state, and the first one was divided into 5, and the bottom one was divided into 3 state. And let's suppose that if the rubidium atom is in F1 here, in any of this is red with the spin up, and if it is in F2, we will show it with the green color. So that is the basic understanding. Now what happens is that once something excited state to this state, which is, or let's say from F2 to F1, then they change the direction of precession. So if they were doing something like this, and then suddenly they will reverse and do something like that. So the geometric ratio is opposite. If atom moves from F2 to F1, and then the precession will start happening in the opposite direction. So these are three basic conditions we first assume that is there. So F1 we show with red color, F2 we show with green color, and suppose they were moving like this in case of F2. Once they jump from F2 to F1, they will start precession like this. Okay, let's now first discuss when we have a high magnetic field. So in case of high magnetic field, if two atoms both were sitting in F2, denoted with green color, and their spin is up, right? And now if they both are sitting there and they are doing this kind of precession, right? They are moving in clockwise direction. Now suppose some collision happened between these two themselves, so the collision between the rubidium atoms. So because of the collision, they will come from F2 to F1, and once they come from F2 to F1, the first thing is that the color will change red, and what happens next is that this will move in the same direction, but the another one will move in the opposite direction, right? So this whole thing actually depolarized the system, and you see that once the collision will start keep happening, then the spin which was like this, it will first convert into the red, and the spin state will change a bit, and then further changes and further changes. So the total ensemble, if it has a magnetic moment or polarization in a particular direction, it will slowly start reducing, and the whole macroscopically the ensemble will rapidly lose its coherence, or you could say it will lose its spin. Now let's say you are in this another regime where we use low magnetic field or SURF regime. What happened in this regime? Let's say some atom which was sitting in F2, and now it will come back to F1 because of the collision. So it will collide with another which is in F2, and then it will come into the F1 state. And that is the total polarization or total spin direction of the whole ensemble of rubidium atom. It is something like this. So what happens is that, so you will, I hope it works. Okay, give me 1 minute. Um, So what you see is that, let's say in the beginning, it was like this, right? It was in the F2 state. As soon as the collision happens, it comes to F1 state, right? So once it comes to F1 state, the color changes. And also you have to see that when it was rotating like this, now it will change its position and it will start rotating in the other direction. So because of that, you see that the total spin cannot really move in the other direction. So as soon as it tries to go in the other direction, the collision happens and then it quickly comes back to the previous direction and then again hits back and then try to go here. Then again collision happens and then it comes back. So because of that flipping, it is not possible to completely move into the other direction. So just to show you again, it tries to move in other direction, collision happens, comes back. Then collision happens, again try to go in other direction, then collision happens, it tries to come back. So because of this sort of motion, uh, in this regime, it will be not possible for them to completely, go out of the spin or completely have a different spin direction. So the average ensemble spin remains roughly the same, or the decoherence is very less in these kind of systems because of rubidium-rubidium collision. And this is the most dominant collision actually, because you see the collision with the nitrogen is actually just to avoid that photon, which is unwanted photon. So that is in a way is good. The collision with helium stops the wall collision and all that. So rubidium is the main collision. And since we are working in low magnetic field regime, and where this collision happens very fast as compared to this rate of precision. So this precision is happening slower. As soon as this tries to precise in the other direction, you suddenly get a kick and then you come back to your original direction and then you start moving like this. Once you're moving like this, you come hit again and then you try to suddenly move down and then you see that okay, somebody hits again and then you come back to your original state. So that is the main concept behind working in surf regime, that the coherence time is quite nice as compared to high magnetic field regime. Um, so I mean, I told you, this is all about this surf regime that we somehow able to maintain even after the collision. This red color, you see that the spin is same. What is the spin in the green color, even after a lot of collision. So we started with similar spin. This tries to move a bit in this direction, but suddenly it gets a hit and then it moves back in the counter direction. And similar things happen to this. It was moving here and suddenly it gets a hit, it moves here, and then you see that they are both in roughly the same direction. Now by doing that in this regime, they have claimed a very high sensitivity, which is roughly 160 attotesla, meaning 10 to the power minus 18 tesla. That is the record up to now, the minimum magnetic field which is being captured or measured. And as you know that in all these quantum systems, because see, spin is also quantized. So if you know about the Stern-Gerlach experiment and all that, you will find out that spin is also a quantized thing. And in all these quantum systems, we are always limited with the short noise or some sort of noise. So there are different noises. So in this system also, you are working already in the short noise limit regime, like you are going below the noise. So noise is already up to 0.1 femtotesla, and you try to go below that, and you try to measure this. So that is the surf in a 6 mm cube. So if you take a smaller cell, so see, if bigger the cell, you get high sensitivity. You make the size smaller, less number of alkali atoms, you are able to measure less sensitivity. So in this much of size, they were able to measure 5 femto tesla per hertz square root. So here is the graph where you could see the magnetic field. So in Gauss, and you see that the surf regime works in the areas where the magnetic field is quite weak, 10 to the power minus 6, minus 5. As soon as you increase the magnetic field, you go into the traditional magnetometer regime, and here you see the FWHM, the full width half maxima, is quite broad in all these systems. And in this case, it is roughly 0.8 or something like that. And in here, it might be 100. So they are quite broad in nature, and that's why sensitivity is lower. And here the sensitivity is quite good because sensitivity is inversely proportional to the FWHM. So after all this, we now have to see like, okay, how we, so I told you we have this atomic vapor inside a cell. There are a lot of rubidium atoms. We go with the pump beam. And now I have explained you that we have aligned all these rubidium atom in one particular spin state. They are all in one particular spin state. And there are a lot of factors which create decoherence. We got some idea about them, such as collision, nitrogen collision, some photon generation, which was unwanted. But we know that, okay, even after that, these atomic magnetometer, they can create femtotesla field. And now suppose if you apply the magnetic field and you try to probe that magnetic field. So in the beginning, I told you there is also a probe beam. So how that probing works? So let's say that is this rubidium atoms inside this cell. What you do is you come up with a probe beam which is polarized like this, linearly polarized light. Once it goes through this rubidium atoms inside this cell, finally the overall polarization will rotate with an angle theta. And why this happens? So actually, there is a long theory behind that. Is that this rubidium atoms actually, for a circularly polarized light, they act as a birefringent medium or material. So what is birefringent material? Is that in two different directions, the refractive index of material is different. Let's say in x-axis and y-axis, the light propagates in x may be faster because the index was lower, and in y the light propagates slower because the index was more. So because of that, you create the birefringent property, and you see that if two things are moving slow in one direction and fast in other direction, in the end you will see some sort of phase delay, and because of that phase delay you can have some sort of rotation. So that is the reason these things, rubidium atoms, they act as a birefringent medium, and then they create this kind of rotation to a linearly polarized light. Remember that I told you that this light has to go perpendicular to the pump light, so we cannot operate in the same direction. We have to go in the orthogonal direction with the pump beam. Um, so its plane of polarization will be rotated, which is dependent on the net spin, which is dependent on the rubidium atoms. What is the spin, total spin of those atoms? And due to a refractive index difference in sigma plus and sigma minus, these are two circularly polarized lights. So what they want to say is that this circularly polarized light which you are incidenting, it can actually, so the linearly polarized light, sorry, which you are incidenting can have a, you can represent it with a combination of LCP and RCP. So LCP plus RCP is equal to a linearly polarized light, and this medium acts as a birefringent medium for LCP and RCP. And you, as I said, you will see that two different directions have different refractive indices, and then because of that, finally there will be a rotation in the angle. So that is the basic principle why the probe beam rotates in a particular direction. Now there is a technique called optical polarimetry. So we have to now apply this technique to actually measure something. So what we do is that we have this probe laser, and as I said, we apply this linearly polarized light. So we apply linear polarizer, and then the light will be linearly polarized. Now this light will go through this cell, and then this light will take some sort of particular rotation because of this region. Because of this, the light will rotate in some direction, right? Because of this birefringence and all that. Now what we have to do is that we apply the beam splitter, and this is a 50-50 beam splitter, and we have already aligned the direction at 45 degree. So what it will do is that half of the light will pass through this polarization. So this is not a normal beam splitter, it is a polarization beam splitter. So it will polarize the light. So half of the light will polarize through it, and then this light will go to one of the photodiodes. And this is the another photodiode. So this is some kind of a sort of homodyne detection. And that what you are doing is that the intensity which is coming here, you are dividing it into I1 and I2 into two different intensities. And by applying this particular formula, because the interference will happen, and then you can see that I1 minus I2, you know all these values, and you can actually calculate how much was the rotation into this beam when it came out. So linearly polarized light, because in the cell you will feel the birefringence, and because of that birefringence there will be some theta. This theta will be associated with the spin of these rubidium atoms. That spin will come due to the applied magnetic field. So if we are able to calculate this theta, which we will do by applying these photodiodes and a beam splitter, and finally we can actually calculate this theta, which comes out roughly 10 to the power minus 8 radian. So if you can calculate theta, then you can actually also calculate B. In the beginning, I told you the equation that you can apply that equation and back calculate the B value. So this is all about the mechanism of the atomic magnetometry. So that's how the magnetometer works. And now we can take some questions, and after that we will take a 5 minutes break, and then let's continue further. So please write your questions in the chat. Okay, let me go back. So I think there is a question here that why the diffusion from the wall has a positive sign here. I think this is what someone has asked when we have the total polarization of the ensemble, and we want to see how it changes with time. So one is doing some precision because of magnetic field, and then there are some collisions, and uh, it's a valid point that you see that because of the pumping, you have rate of pumping, and you multiply with the vector. This is the S is the circularly polarized light vector, but you subtract this P part, and this P is the rate of the photons which is coming down. So all the time we have kept minus when the things are creating problems. But here you have to understand that when we do this double integral del square p, in the end there will be a minus sign which is already associated here. So once you open this double differential equation to try to solve it for the p, you will see that there will be a minus sign which is already incorporated in D. So that is why we have not, I mean, this, I have not written it, but they have explicitly not written a negative sign, but this is, I hope, already incorporated in the D itself. So are there any more questions? Okay, you can still keep writing if you have more questions, and I will try to answer. And let's take a break of 5 minutes, and then we come back at 3:10.